In this video, we are going to talk about how floating point numbers are represented, how negative values are handled, and how they are represented in computer using IEEE 754 standard. Okay, first we examine how to convert floating point numbers from base 10 to base 2. Suppose we have the numbers 12.125. This number consists of two parts, an integer part and a fractional part. And you can see the positional values of each digit in base 10 as follows. For the integer part, we have 10 to the power of 0, 10 to the power of 1. And for the fractional part, we have 10 to the power of minus 1, 10 to the power of minus 2, and 10 to the power of minus 3. Now, if you calculate the sum of digits multiplied by their positional values, the result will be 12.125. Now, if you want to represent this number in base 2, for the integer part we need to use the method of the successive division by 2. 12 divided by 2 equals 6, remainder 0. 6 divided by 2 equals 3, again remainder 0. 3 divided by 2 equals 1, remainder 1. And finally, 1 divided by 2 equals 0 with the remainder 1. Now, if you write the reminders from bottom to top, the binary representation of the integer part is obtained, which is equal to 01100. Here, I added the leading 0 to indicate the sign bit, which shows that the number is positive, since the 0 indicates that number is positive. Now, how do we convert the fractional part of a number to base 2? For this, we can use the method of successive multiplication of the fractional part by 2, continuing until we reach the whole integer with the no fractional part. Here we have 0.125 times 2 equals 0.25, where the integer part of the result is 0. 0.25 times 2 equals 0.5, where again the integer part is 0. And finally, 0.5 times 2 equals 1.0, where the integer part is 1 and the fractional part is 0. Now, if we write the integer part from top to bottom, the binary representation of the fractional part of the number is obtained, which is equal to 001. And as you can see, the representation of the number 12.125 in base 2 is 01100.001. Now, if we want to represent the same number as negative, we need to find the 2's complement of the number. To do this, we first find the 1's complement by flipping all the bits. The number 12.125 in base 2 is 01100.001. So after flipping all the bits, it becomes 10011.110. Now, we add 1 to the 1's complement to get 2's complement. This 2's complement is the binary representation of minus 12.125. Now we have a standard that tells us how to represent and store floating point numbers in a computer. This is the standard is IEEE 754. First, we need to normalize the binary numbers and write it in scientific notation. To do this, we shift the decimal point left or right until only one integer digit remains. For our number, we need to shift 4 times to the left, and the result becomes 1.0011111. Now we write the number in scientific form using the base, which here is 2 raised to the power of the number of shifts, which is 4. Next, we use the IEEE 754 standard to store the number. For this, we have 1 bit to store the sign, 8 bits to store the exponent, 23 bits to store the Mantissa. Let us start with the sign. Since our number is negative, we store 1 in the sign bit. If the number were positive, we would store 0. Now, how do we store the exponent? The number 4 obtained from shifting is added to 127, which is the bias. We will explain later what the bias is and why it is 127 here. As you can see, 100 plus 4 equals 131. The binary representation of this is 1000011. This is exactly what we store in the 8-bit exponent. Finally, for the Mantissa, we store the fractional digits. As I mentioned before, I want to explain what is the bias and why is it 127. And also, why do we have to add the bias to exponent? Bias is a fixed constant that is added to the real exponent so it can be stored as an unsigned number. In the IEEE 754 standard, the exponent is not stored directly with a positive or negative sign. Instead, it is always stored in a bias form. Now, why do we add the bias to the exponent? Because the exponent can be negative for very small numbers or positive for very large numbers. But the exponent field in IEEE 754 is an unsigned field. If we store the exponent directly, we would need a separate sign bit for it, which would make hardware design more complex and comparisons between numbers harder. By using a bias, all exponent values become non-negative, making storage and comparison simple and efficient. Now, why is the bias value 127 in single precision? In single precision, the exponent is stored in 8 bits. An 8 bits unsigned number can represent value from 0 to 255. From this range, the values 0 and 255 are reserved for special cases such as 0, infinity, and NaN. The values 1 to 254 are used for normal exponent. If we look at the middle of this usable range, the number 127 is approximately the center. By choosing a bias of 127, the smallest normal exponent is 1 minus 127 equals minus 126. And the largest normal exponent is 254 minus 127 equals 127. This gives a balanced representation for both very small and very large number. That's why we add the bias to the real exponent. It simplifies storage, speeds up comparisons, and makes the overall system more efficient.